Hey friends, it's Derek from Tech Connection, and in this video we're going to level up our routing knowledge one more time. In our last video we talked a little bit about creating static routes in order to get through multiple networks. One of the things that I said in that last video is a throwaway line where I mentioned that routers don't automatically exchange information about their routing tables unless they've been configured to do so. And then I proceeded to show you how to do it manually. In this video, we're going to talk about ways to automatically exchange routing tables between multiple routers, not just two. We're going to take this to the next level. I'm going to put a ton of routers together in our lab, which is going to be a really fun time, and we're going to have them all exchanging their routing tables. Now, in order to do that, there's two different software packages that you might utilize in order to configure these two routers. One of them is OSPF and the other is BGP. Those two are Open Shortest Path First, which is a routing protocol that allows routers to exchange information, and the other one is the Border Gateway Protocol, which allows routers to exchange routing information. So which one do we use? Well, it's commonly held that if you're just working within a single institution, that you should use OSPF, and you could use that to exchange private subnet information between your own routers and public IP information for routers that are at the fringe of your network. Think of like where maybe you've got a faraway house, there's a fiber strand leading all the way to the edge of what constitutes your network, and you want to give a public IP to that equipment that's there, but everything in between that equipment and your main facility is private subnets. Well, you can still use OSPF to exchange information about where you're keeping your own public IPs within your own network. But when it comes to exchanging that information with another institution, Border Gateway Protocol is preferred. Normally, BGP is used when you are Verizon and the other guys are Sprint, and where your two networks touch. You'd like to exchange information so that packets that need to route don't need to go through a third party. You could short circuit that and pass it directly to each other. BGP is for institutions that are usually ISP level or greater in size, and they're typically meant to route large networks of public IP information. With that having been said, obviously for this lab and for this explanation, I'm going to be using OSPF mostly to show how to do private subnets, but you can still use it. Keep in the back of your mind, public subnets are okay to use with OSPF. Now I'm about to cut over to our lab, and our lab is going to be a little bit interesting. So I want to point out the router that I'm using is an EdgeRouter. EdgeRouter is a router that I'm using because it is incredibly simple. It's quite outdated by any modern standards as the time that I'm filming this, but for learning purposes, it's fine. It's perfectly good. However, I don't think that's enough learning, so I'm also going to include a MikroTik router board. This is a 5009, and the router board is a much different way of configuring a router. There's different rules, different operating system, different everything. And if we can get these two very different machines to exchange information about their routing tables, then that will be a useful learning process for us to go through. So that's going to be part of our lab, is I'm going to mix brands a little bit. Now, what should you do if you don't have enough equipment to follow along with me in the lab? There's nothing wrong with that. I have a couple suggestions. One, look on eBay and grab up some old MikroTiks. You could get the hex routers that are like 50 bucks, and you could probably find some used ones on eBay in a lot of 5 or 10. If you can't find a used lot, get together with some friends. Surely you can't be the only person you know that wants to learn networking. Get with some friends. Everybody buy a router that at least has OSPF as a feature, and then let's have a LAN party, guys. Get all your friends together, learn how to do the configuration between all your various models, and I guarantee you will go further than you ever thought just trying to troubleshoot it around the patio with some friends and some laptops. And then when you're done, hey, LAN party, right? Okay, I'm going to cut to that lab, and we're going to set up a bunch of routers, and you're going to see exactly how I create a situation where they're exchanging information. Hi students, welcome to our lab. For the lab, we're going to be building a meshed network out of these routers here. I do have the one router board as promised, and the rest will be just the standard edge routers that are easy to configure. We're going to be creating a mesh, which you might think of more as an intranet. I am simulating in this lab something like a university campus, perhaps a hospital facility, or even a military base, something where there are many departments, many networks, things like that that you have to interconnect between buildings. That's what this is going to be. Now, before I build this, it would be a good idea to get a piece of paper and sketch out what my plan of attack is. So let me do that for you right now. All right, here's my drawing of the mesh that we plan to build. In the center of our network will be 4 routers and then 1 router on opposite ends of our network. Representing right here, this laptop will be representing our first LAN, and this last laptop up here will be representing our final LAN. And in between will be the intranet. And we will be disconnecting individual segments to see how the network reacts and whether it is able to still pass information reliably. Now, each one of these line segments represents a LAN. So let me show you what I mean by that. So each line segment on that drawing represents a point-to-point LAN. What we're going to be doing is patching in one router interface to its neighbor router interface. This requires 2 IP addresses, one for this interface and one for that interface. Now, what you've seen me do in the past, whenever we've done one of these labs, is I've used a mask of 255.255.255.0. And in order for that to work, whenever I needed another LAN, it forced me to change the 3rd octet. So I'd have 192.168.1.0, 2.0, 3.0 in the previous lab. And if you look at all the links that are showing on our diagram of what we plan to build, we're going to need 4.0, 5.0, 6.0, 7.0, and we're going to be wasting tons and tons of IP address space. Each one of those networks that we declare has 253 host IP addresses available, but we're only going to be using 2, and that's really wasteful. So I'm going to show you a way to level up, which is to change your subnet mask. For the purposes of this lab, we're going to be using the mask of /30. That is 255.255.255.252. That's the next one down. What that is doing is when you're using the standard /24 mask, which is 255.255.255.0, you're actually using 24 bits to represent the network and 8 bits to represent the host. When you use a /30, we're using 30 bits to represent the network and only 2 bits to represent the hosts. That leaves us with exactly 4 IP addresses, one for the network, one for the broadcast, and 2 for the routers themselves. It's the perfect way to slice this up when we're doing point-to-point connections like this. It also preserves all of my private IP addressing range. I can use a single subnet from 192.168.10, and that will represent my routing network, and I will slice it up into little groups of /30s. I never need to change my 3rd octet when I'm doing this because I haven't yet exceeded the number of routers it would take to do so. I'll focus more on subnets in another video. It's a big topic, but you've seen me only do /24s, and in this lab, it's time to move on and learn something new. We're going to do a /30, of course, but keep in mind there's /29, 28, 27. All of these have a purpose and a use that would be advantageous in multiple scenarios. We're going to cover that more in depth one of the next times. But for now, just roll with me. If you've never seen it before and it feels a little weird, follow along and let's see how you do. Now, in order to build this mesh, I'm going to need a lot of power cords, a lot of patch cables, and for demonstration purposes, I'm going to try to physically lay it out on these shelves the way that I've drawn it on this mesh. If you wanted to, you could just stack them. If you're in your own home, just as a visual aid, I'm looking to make my drawing and my actual built network match. That way you can follow along a little bit more easily. So let me get all of this plugged in. All right, hard to believe, but we've matched the drawing physically. I hope you're able to follow along. In order to simplify matters, I'm going to overlay on the screen the networks that I create, because I think otherwise it'll be very difficult to follow along with this. Why don't we start configuring the IP addresses of these interfaces right now? I'm going to draw it into my diagram and then put that on the screen for you. All right, I'm going to connect my laptop to each of these routers on the shelf, and I'm going to configure all of those interfaces to match everything in my diagram. That's going to take me a bit of time, so I'm just going to cut to that being finished already. All right, I've got all my IP addresses assigned to every single Ethernet port on every single one of these routers. Now, the next thing to do is configure OSPF in order to let these suckers trade routing tables with each other automatically. Let's go ahead and configure that on this first router, and then you can just extrapolate what to do on all the others. So in the EdgeRouter dashboard, where you want to go is to this tab called Routing. When you go into Routing, it will show your routing table. There is a sub-tab called OSPF that you'll want to click into. Now, there are three things needed in order to make OSPF work. One, your router must have an identity or some sort of identifying number. Most of the time, I set this to the IP address that I consider the management IP address. With nothing else known about this router, if I can't determine what IP I should use, I pick the lowest Ethernet port's IP address and I just go with that. So the identity that I will give it will be 192.168.10.34. That is my router ID. No two routers within my mesh should have the same ID. Next up, there are two checkboxes that look interesting. Let's take a look at those. They say redistribute connected and redistribute static. What this means is whatever Ethernet networks this router is connected to, it will share with its friend and neighbor routers if I checkmark that box. Otherwise, it will only share the networks that I manually assign. Normally, you do want to press that checkmark on. The next one is for redistributing static routes. If you've manually been adding routes to your router and you want to share those to the rest of the entire network, then you can do so there. This checkmark here for announce default route, if you checkmark this, you're telling the network that this router is the one that's connected to the ISP for your entire zone. If you've got a college campus, one of your buildings is probably connected to the full internet through an ISP that's maybe delivering 10 gigs or 40 gigs to your campus. Whatever router's connected to that should checkmark announce default route. It tells the rest of the routers which router in the mesh is connected to the internet, and the rest of them assume that they are not. Only one router in your network should have this turned on, if any. The next piece of information that OSPF needs in order to function is which interfaces it should broadcast on. Over here on the EdgeRouter screen, there is a section for interfaces. If you click Add OSPF Interface, you are able to choose which Ethernet ports are participating in the OSPF trading of routing tables. If you leave an interface off of this list, then what will happen is your router will ignore any OSPF requests it sees come in on that interface. For the purposes of this lab, I'm going to add every single interface to this list because I want the mesh to happen amongst all of the ports that I have plugged in. However, in the real world, you would choose carefully which ports should send and receive OSPF information. The final piece of information that OSPF is going to need for our lab is it needs to know what is called the area ID. In OSPF terms, an area defines the group of routers that actually exchange information. If you have so many routers going on in your organization that you end up needing to segregate it so that routes from faraway sections of your campus don't need to bleed all the way to from one end to the other. Maybe you have a west part of your campus and an east part of your campus, you would segregate by area. For our lab, we're just going to have a single area and we're going to exchange routes between every router that we have in that same area. Therefore, we're going to click Add Area. The area ID is going to just be, for this situation, all zeros. Then, in the area screen, there's also a field marked Network. Here, you can place network entries that you would like to announce to your neighboring routers that they can add to their routing tables. The EdgeRouter will automatically redistribute all connected interfaces if you checkmark the Connected Interfaces button. However, if you've not connected it, you'll have to manually add all of the networks you wish to announce in this box. The EdgeRouter has a quirk where you must add at least something, even if you've checkmarked the redistribute connected items. So what I do is I pick the lowest numbered Ethernet interface, such as Ethernet 0, and whatever network I've assigned to that, I put into this box here. Okay, to configure OSPF on the MikroTik, the first thing you're going to want to do is go down to the IP section, click on Firewall, and make sure that you've cleared all of the default firewall settings, because these will interfere with the OSPF configuration that we're about to do. You'll also want to go into NAT and make sure that there are no entries there. The default settings in a MikroTik are going to conflict with what we need to configure. With those removed, go down to Routing and then pick OSPF. We need to create a new instance of OSPF. All the default settings are fine, except for the router ID needs to be changed to be what we think is the management IP. For our particular diagram, it's going to be 30. Now that we've got an instance going, we're going to create an area. So for the area, normally we name this something like backbone. At least that's what I see everyone else doing, so why be different? Area ID needs to match what the edge routers are showing. We're going to make that area take effect, and then under Instant Interface Templates, we're going to add a new one. The area will be backbone. Now, let's take a close look. Before we make some entries here, there's an entry for network and an entry for interfaces. Let's quickly look over at the OSPF instance where it says what to redistribute. These are the same as the checkboxes on the edge router. So if you have this connected box checked, then you will not need to list all of your networks that you want to advertise. But if you have this unchecked, you'll need to manually specify every network that you want to share via the OSPF protocol. I'm going to check mark connected, and that means when I'm making an interface template, the only thing I need to do is pick out, let's make a few of these, pick out which Ethernet interfaces I want to broadcast. Oops, that should be 4. And that should be 5. So I'm going to broadcast routing information on these interfaces, and I don't need to specify which networks I want to announce because I have that check mark on. Everything else being default is just fine. So now let's quickly look over. We've made an area. We've made interface templates, and if we look here, we can see what state each of my interfaces is in, where they are broadcasting. That means if I go over to neighbors, I'm going to see what's called adjacencies. This means that we're successfully in communication with the edge routers that are on the other end of those interfaces. To confirm that everything is working correctly, I'm going to press IP, and I'm going to go down here to routes, and then we're going to have a much bigger routing table, and the source of these is going to show you which edge router they got that information from and what the route was. If there is an O flag showing here, that means we got this through the OSPF. All of this is normal, and now we have a full meshed network where we even mixed brands. All right, friends, I've got everything meshed together. I've confirmed on the laptop that all of my routers have matching routing tables, so they're all exchanging information automatically. And now I've got a laptop added at the top of our mesh network, and I've got another laptop on the bottom. So for these two laptops to communicate, they must pass through this mesh one way or the other. And let's start with the IP addresses. This one is 192.168.2.100, and this is 192.168.1.100. So the first thing that we do when we want to check connectivity is we just try to ping each other. I should be able, from either laptop, I should be able to ping the laptop, but I can also target any of the IPs that I assign to any of these interfaces anywhere. So I ought to be able to ping all of the 192.168.10 style subdivided networks, as well as the laptops. Let's give that a try right now. So that's going to be ping 192.168.2.100, and I get a reply. And just to confirm that I'm able to ping one of the routers at random, I'll ping 192.168.10, and let's pick something over here, 17. So I picked a random interface, and I'm able to ping that as well. So we've got ourselves the perfect setup to make a really interesting lab. Now, if you weren't able to follow along with me and build something quite this big, build the biggest thing that you can. I would say 3 routers would be at least a good sized lab for somebody in their home. You don't have to make something as ridiculous as I've made. And if you've seen any videos where somebody did more than 6 or so routers, please link it to me. I'd really like to see that. I'm always looking for ideas for a good lab. This takes forever to set up. So getting any bigger than this would be a little bit ridiculous, but it's really useful for students. And here is something that you should learn right away. I think you already know it, but I'm going to reintroduce it. If you've been doing a little bit of networking, you're going to be familiar. It's traceroute. So traceroute shows which interfaces my packets go through on the way to their destination. And you probably already knew that, but now that we have a visual layout of how these routers are interconnected, traceroute's going to make a lot more sense than it does when you just see it on paper. Let me show you what I mean by that. I'm going to type traceRT. I'm going to give it the D parameter, which means it will not try to convert any of this into domain names. And then I'm going to target the laptop at the very end of my network. And what will happen is traceroute will show me all the interfaces in my mesh network that were used to forward the traffic to the target. And all of these are possible because of OSPF helping my routers learn where the next location is that they should be forwarding their information. If you visualize that text output, it's basically going from this router to this router to this router to this router to the laptop. How does OSPF decide which interface to use? It's going to depend on a couple of different factors. One of the factors is bandwidth. How fast is the link between these two routers? If it's 100 megabits or 10 megabits, it'll be less commonly desired over something that's a gigabit. So that makes sense. It will use the fastest link it can find. The other thing it will use is when you were configuring OSPF and you were creating the networks that you wanted to share, there was a metric there that said distance, or in some cases it just says metric, depending on the brand of equipment that you're using. If you mark something as being high distance, then that will be less favored over something that is low distance. We don't often use that, but it is something you can use to force traffic to go a particular direction. Times you might want to do something like that is when your router equipment is got a gigabit link, but maybe not such a great throughput, not such a great CPU. In a scenario where it struggles to pass information at wire speed, you might only use that equipment as a fallback and set the distance metric a little higher so that OSPF will not favor that pathway. Now, let's have some fun, shall we? Let's do a little bit of work here. I'm going to start a continuous ping running to that laptop from that laptop. And let's interrupt the chain and see what happens. So that's going to be ping 192.168.2.100 and -T so that this ping never ends. We already know from the previous trace route that it goes from this router to this router. What happens if I unplug it in the middle of a ping? So I've got active data flows that are in progress. Let's keep an eye on my ping and see what happens. It's timing out, but then it recovers. This is called convergence. What's happening here is OSPF every so often synchronizes or resends the routing tables. If a link light has actually gone out, then that interface will be removed from the routing table. Whenever let's pop that back in. Whenever it changes, there will be an effect on your data flow. You'll lose some packets, at least one, but then the system will recover. Let's translate that to a bigger network like I did in the previous video. Let's say we've got a college campus. You'll see here that I labeled all of these student services, biology lab, and so on and so forth. If we overlay this network over a college campus, for instance, you wouldn't want something going wrong at one of the buildings to impact overall network reachability throughout your entire campus. That is why in my diagram and in my physical build, everything is plugged into everything as much as I could possibly make that happen. And only on the fringes are we down to 2 links, but the inner routers have 4 links between each other. That means they can recover from almost any outage scenario short of leveling a building. So if we've still got some network reachability, the OSPF software always works out the best way to get to the target. Now, with this unplugged, let's do another trace route and see what happens. So we're seeing now that the data took a different pathway. It went from this router sideways. Then it went to 26. That's this router. So we've gone up diagonal, then to this one, then to the target. So that should give you some idea. If you do some playing around and unplug things while pings are in progress or other data flows, downloads for instance, you're going to see how quickly OSPF is able to converge. It's not magic. It isn't able to deal very well with constant outages. So if things are being moved a lot, OSPF is going to drop packets like crazy. So it's not the same as, say, VRRP, VERP, or other high availability techniques. This is more of an adaptability solution. So when OSPF is able to, on its own schedule, make adjustments to the pathing, that's different than high availability where you have 2 routers working in concert together to ensure that packets are not dropped. Packets do get dropped when there's network interruption on the OSPF routing system. Now, as we near the end of our lab, let's discuss a couple of things that might get you in trouble when you're in a business environment. One of those is that redistribute connected checkmark that I've done on all of these routers. You'll find in the real world, you're probably not going to want to have that happen. That will distribute information about your network to parties that you can't necessarily control. It will also have the unintended side effect of distributing networks that you don't even know about. If something is attached to your network, it will be redistributed, but you may not have been aware that that happened. It's better in most cases not to distribute things that are connected as a check mark, and instead you should declare them in the area ID as something that you want to announce. That way you retain control. There are such things as routing loops, so it would be an interesting experience for you if you were to give the same subnet and same LAN information to 2 sections of your routing network. So if you've got one end has the same subnet as another end, what happens to those routing tables when OSPF exchanges that information? To recap some of the terms that I've used in this video. Adjacency. That is when one router and another agree to exchange tables. They have formed an adjacency. Convergence. Convergence is when the entire network has agreed what the routing tables should be. If there is a change in the network status because something has failed or been unplugged, convergence is also an amount of time it will take for everything to agree again. OSPF is relatively fast at convergence, but it is not a replacement for high availability. That should cover it for this lab. If you've built this at home, leave it connected and play with it. This is a great way to test all your future endeavors when you're setting up software, websites, DNS. You've already built the skeleton and framework, and I think you'll find it's really useful. I'm gonna finish up here. I got a lot to clean up, as you can see, and I'll see you back at the office in just a sec. So that was one of the biggest labs that I've ever done, and it's something that I usually save for the end of a networking course, but I hope that you got a lot out of that. It's very rare that you'll get the opportunity to put that much equipment together in a commercial setting. So doing it as a lab in this scenario, you'd be shocked where that knowledge carries over into your future commercial endeavors or in your career or in your schooling, etc. I want you to think about, like in my previous example, where there's a college campus with a bunch of different buildings, 20, 30 different buildings. That's the kind of situation in which the lab that I've shown is something you might try to implement on your own. If you're working for the IT team or you've got like an internship somewhere, try and take advantage of the knowledge that you've got here and flex your muscles a little bit. It's important when you do something like that for an institution where you're the only one doing the learning and therefore the only one implementing those technologies, to write everything down so that the next person after you can benefit from what you've created. Otherwise, if you just disappear and move on to your next job, you've left behind a little something we call technical debt, and you don't want to do that to your next person in line that follows after you. Try to leave something behind documenting what you did, and they can start learning on their way through their journey as well. Well, I hope that's been interesting. I appreciate that you watched this, and I will see you again real soon because we've got another lab dealing with more network topics related to routers. All right, until then, happy network.